This is Jack Jackson. We want to look at an application of the side angle side postulate today. And we're going to apply this to a isosceles triangle. Now remember, an isosceles triangle is by definition a triangle in which it has two congruent sides within the same triangle. So these two red sides here are congruent to each other. And we already noticed this in an earlier video, is that it turns out that these angles here are congruent. In fact, in general in a triangle, the largest angle is opposite the longest side, and the shortest angle is opposite the shortest side. So when you get a tie, so the two sides are the same length, it turns out the two opposite angles are the same length. But we can actually prove that now that we have the side angle side postulate. And what we're going to do is prove that this triangle is congruent to itself. Now, of course, every triangle is congruent to itself with the regular correspondence. In other words, triangle ABC is congruent to triangle ABC, where, A corresponds to A, B to B, and C to C. But this one is congruent in a different way. Triangle ABC is congruent to triangle CBA. In other words, it's congruent to itself with a flip. So we know that side AB is congruent to side BC, and then angle B is congruent to angle B, and then side BC is congruent to AC. So that's side angle side within the same triangle. It has a side, then the angle, and then the side. And so it's congruent to itself with this flip, and that means, of course, this side is congruent to itself, which is nothing new, but that proves, though, that these corresponding angles here and here must also be congruent. Turns out that it works the other way, but we'll see this a little bit later on. When we get to isosceles 2, we'll show the proof the other way, that if you have these two angles congruent, then the sides have to be congruent as well. Now, of course, an equilateral triangle is an isosceles triangle, so we have a corollary. Corollary is a theorem that comes kind of directly from another theorem. And we can prove then that every equilateral triangle must also be equiangular. So the proof goes like this. Since we have an isosceles triangle here with these two sides congruent, these two angles must be congruent. But it's also isosceles this way with these two congruent sides, so these two angles are congruent. And so this angle F is congruent to both D and E, so actually all three angles are congruent to each other. And of course that means by the angle sum theorem, they must all measure the same, and they must sum up to pi radians, so the measure of each of the angles is actually pi over 3, or in degrees, the angles add up to 180 degrees, and we divide that by equally in 3 ways. That means each angle must be 60 degrees. So if it's an equilateral triangle, it's also equiangular. And again, in the second part down here in isosceles 2, we'll prove it the other direction, that if it's equiangular, it's also equilateral. And so it turns out equilateral triangles always have angles where they're all three 60 degrees. So there's a direct result of the side angle side postulate that tells us something about isosceles and equilateral triangles.